So Sam's title is, I believe, Distinguished Engineer.
Distinguished Engineer, yeah.
At IBM Research. And he's going to talk about superstition and forgetfulness, two properties, two characteristics that he thinks are critical to designing artificial general intelligence systems. So, take it away.
All right, thank you. I want to join all of our other speakers in just expressing our appreciation for everyone who's come and all the fascinating discussion we've already had. We're looking forward to a lot more of that. What my talk's going to focus on is a couple of things. I'm going to talk about what I believe are major challenges and pathways as we try to approach artificial general intelligence, but I'm also going to discuss a project that I was privileged enough to be a part of at IBM between 2000 and 2003, where we were actually allowed to actually go for it and say, okay, let's take all the blinders off and all the chokes off and try to build one. And so we'll talk a little bit about that. But first I want to start with a quote from Rodney Brooks. Has been one of my, this quote's been one of my inspirations over the years, which is something that he made about the time that people were saying, you know, to do robots that can walk, you're going to have to do all this really heavy-duty, monstrous stuff. And then he came along with Genghis, you know, that not only could walk, but taught itself how to walk, could adapt to its environment, could figure out what was going on with itself, even though it was very, very simply coded, but very brilliantly. And I think that that's, you know, the goal here is the last statement there. What my work was about was something that works. How do you get to something that works? The previous speakers have talked about the difficulty of trying to project what's it going to be like if we have a superhuman intelligence or anything like that. I'm not really worried about that. The only proven pathway to human levels of intelligence we have is the one we walked ourselves. So let's go look at that and learn from it and see if we can build something like it. So that's what we'll talk about in between. So major challenges. I think that I'm going to do a little word play here up front, and the colors aren't turning out very nicely, so I'll just read it. But I think we have some major challenges in trying to do understanding, meaning, and common sense in computing. This is a quote by Walter Freeman, who's a very distinguished professor of neurobiology, neurophysiology, that I think says it very well. If a system's actually going to be able to really understand its environment, understand what it can do, and interact in that environment, it's going to have to create a sense of meaning. It's going to have real understanding. And that's something that we really haven't focused on in the AI community and endeavors. And so I played around with the words a little bit to try to give you some of our perspective. So understanding requires an internal system of meanings. Meanings imply outcomes for situations, and all meanings are subjective based on experience. Now, common sense, you know, we're the company that big, you know, built Deep Blue, and we had a 30-year project working on that. IBM's been involved in AI continually ever since the people even started thinking about it. We've always had projects going on in this space because we think it's valuable, one, to track it, and two, to see as advances come along how we can apply it to business. But this quote was a good one. You know, we can beat, you know, Garry Kasparov, but no computer has the common sense of a 6-year-old child. So the question is, why not? Why aren't we focusing on that? See what a child can do. So look at common sense. Common sense implies common sensation, producing common experience. Common experience requires a common embodiment in a common environment. Common environments require common events in a common time frame. You know, when you start talking about computers that can, quote unquote, think 1,000,000 times faster than humans, if you just think for a minute of how much our perception and our cognition is entirely bound to the rate of time that we experience. If it was twice as fast, you know, we've all done this, right? We all, those of us that are young enough to have had record players as children, you know, we took the 78 thing and we turned it on 45, and we thought, oh, isn't that funny? And then we realized that we couldn't understand what they were saying. We are bound to this particular rate of temporality, and if we increase that too dramatically, you know, to think that something that does that is going to be able to think like us 1,000,000 times faster, I really don't know what that means, and I don't think we really understand it. But again, getting back to this, all experience is subjective because all sensation is subjective. So if you look at those things that are innately human about the way human intelligence, human common sense, human understanding, human meaning, human intelligence is about, what does that tell us about what we're going to have to do if we want to reach some sort of general intelligence capability in a machine? So the project that I was one of the investigators on, along with Dr. Nancy Alvarado from UCSD and Steve Burbeck from IBM, was something we call Joshua Blue, and it was to develop a computer system patterned after the human mind that could autonomously learn to successfully function in any number of embodiments and environments. Our approach that we took was to model research findings in developmental psychology and developmental neuroscience, take those things seriously, and look for architectural clues in how human cognition actually develops from early stages, as I said, basically emulating the functional bootstrapping of the human mind, and then going up to about age 3. And the reason we were interested in stopping around age 3 is if you look at what a 3-year-old or a toddler generally can do, they can do all the stuff pretty effortlessly that AI, classical AI says is incredibly hard, right? They can do all kinds of fancy motor control with their bodies. They can speak and understand natural language. They can learn lots of different languages. They understand naive physics. They, can reason. They do all kinds of things. They haven't learned how to read yet, right? They haven't learned how to write yet, typically, except for some really bright kids. But they do all this cool stuff that we think is incredibly hard. So we said, at that point, somewhere between conception and 3 years old, lots of magic happens, lots of juju, So let's go look at that and see what we can find. And to test that, we proposed doing something that we call the toddler Turing test, which we think is a much better measure of this kind of attainment of intelligence. And it's based on standard psychological tests for childhood development. So, from a little more technical perspective, this is the kind of the breadth of what we were shooting for, really to be able to process a network that represents observations, experiences, perspectives, ideals, goals, plans, actions, and emotions, to be able to autonomously acquire common sense knowledge by meaningful self-discovery of the characteristics of the system itself. It has to figure out what it can do and what it's about, the environment that it's in, other systems like itself, and all the relationships between them. And again, I mentioned the measurement of this. And then the other aspect, since we're very focused on Bernie's chart about development, we're very focused on a developmental learning model. We had to come up with a way to scale that kind of learning. Because if you take a system and you say, great, we're going to build a developmental robot, we're going to teach it like an infant, okay, in 20 years you're going to have something interesting. You've got one. Now you could clone its brain and then you'd have 1,000 that were exactly alike. How do you scale that up so you get massive amounts of learning that then you can compress into the same mind? From an engineering perspective, we were looking at creating a general purpose mind, a universal engine that was independent of embodiments, that was self-bootstrapping with minimal a priori knowledge. So you could effectively, the goal would be to put it in a new body, and it would bootstrap up and figure out how to run the body and how to deal with its environment. To have specialized embodiments that had limited interfaces between the mind element and the body, using the model that humans have: sensors, effectors, hedonic events like pain and pleasure, affect, emotional response. And then, as I mentioned, to have this kind of mind meld capability so you could take two of these systems, train them in different environments, and then be able to collect and compose the learning that they had into a new individual that could continue learning. And this is even more detail, but just to point out a couple of things. One of the things we said was critical is if a system is going to attain general intelligence, it has to learn both about what itself can do and have a model of that, as well as what its environment does. And that's where you have two kinds of semiotic feedback for the creation of meaning. You have to get a view of what yourself is capable of doing. Our body is full of sensors that gives our mind constant feedback about where my joints are, what's going on, how I'm feeling, am I hungry, am I tired? As well as getting a model of what's going on out in the world. Another aspect of this that we found really important was really a deep integration of emotion as a control system. The system's based on emotional cognitive principles that we developed and also applied from lots of work done from the researchers in this area around the world. And we found that was a very fruitful way to add human-style behavior into one of these systems, at least at the level that we were working, which arguably was very primitive. Now, I said that we went and we looked at the data from developmental psychology and neuroscience. This is a very busy chart, and in fact, the neuron density curve showed up in black, which doesn't help. But But if you look at this, we went and looked over the literature, and then we tried to map it all onto a chart like this that says, okay, you got 0, you got conception. After that, you got birth. Now, in the meantime, lots of interesting stuff's going on. There are cells, there's differentiation, there's neurons, there's connections, things start happening. And then there's birth, and then, you have a few, really the first year of life, and then things start accelerating out to adulthood. And what was interesting about this, and, on the vertical axis, we have like human level. So, for instance, neuron density at birth is roughly human adult neuron density. We don't have massively different amounts of neurons as we grow older. There is some case for replacement and some other things they found with glial cells, but in general, we have that same amount. Almost all the other parameters we were looking at, language acquisition, eye focus and tracking, the bringing online of various sensory modalities and the integration of those, touch and balance and smell and everything else, followed kind of a normal growth curve where it started low and it went up high. But we found a couple of things that didn't, and that really gave us an interesting insight. There's several researchers that have looked at synaptic densities. So how many synapses are there at any one time in life and what goes on? And these things didn't follow that curve. And so we said, something's interesting going on. So Peter Hudenlacher did a couple of interesting studies that are reflected in 2 curves on this chart. One was looking at synaptic density in the visual cortex. Now, general idea right now is the synapses is where the action is, and that's where in effect, groups of synapses, connections across neurons form the basis for memory and engrams and things like that. So we said, if there's a lot of synapses, then there's a lot of information memories or something, and if those go away, you lose some. So he found by measuring synaptic density in the visual cortex that in the first few months of life, about the first year, there's huge numbers of synapses over and above what an adult has, and then it drops off. Well, why is that? Even more fascinating was what happened to the synaptic density in the neocortex, which he said at birth, there's roughly the same density of synapses in a child as an adult, but within about 2 to 3 months, 50% of them are gone. Now, why in the world would that be? If that's where the knowledge is stored, if that's where the information is, what's the engineering view, which I'm an engineer, I look at how things work. What's the good reason for having that work that way? And we'll talk a little bit more about that later, but we started looking at this and we said, okay, let's take a little bit different view of kind of cognitive development, and we'll look at synapses like they're an entity as opposed to just a place where 2 neuron trees kind of rub together and form a knob. So we started thinking of them in terms of a life cycle. And we said, okay, let's talk about synaptic birth. So synaptic birth occurs when 2 neurons fire in close proximity temporally and physically. So, they're rubbing up against each other, they fire, and they start forming a connection. And that's basically Hebb's rule and the work that he did on cell assemblies. Without any additional stimulation, without any different co-occurrent firing, that connection weakens and dissolves. As it grows stronger over time, that connection grows stronger because the 2 neurons are firing coincidentally within the same time periods. The synapse ages over time based on the experience, in other words, the firing experience of the neurons that are there, and also its chemical environment around it. And there's all kinds of issues when we look at things like psychoactive drugs. They affect that chemical environment. They affect what's going on with the neurons. And then some synapses live as long as they're neurons. We're really glad for that. You don't forget your name, hopefully, throughout your life. In the end, we may have some problem with that. But some are actually killed off in global plasticity events, global events where lots and lots of these synapses go away, and we've seen evidence for that. So we applied this model not only to synapses, but large assemblies of neurons, and said, okay, if that's kind of what's going on architecturally in the kind of information creation and effectively garbage collection space for you programmers out there, what does that mean? What can we use it for? So in the Joshua Blue system, we took a special kind of semantic network, and we applied this same kind of model, the same kind of life cycle model, in the context of emotional cognition is something we call a meta-semantic network, which I won't get into details of. You'll be thankful for. So superstition and forgetfulness, what did we learn? A lot of counterintuitive things. We were really surprised by just taking seriously, as an engineer, looking seriously about how human cognition comes about, and then trying to find analogs of doing something similar in a computer system. So one of the things we found was superstition. Stevie Wonder's great, but he's wrong. we believe all kinds of stuff that we don't understand. In fact, everything you ever learn starts out as a first-time experience that you have no clue if it's ever going to repeat. Now, if you think about what it takes to learn how to function in an environment and learn how to be successful in meeting your own goals, you have to build a pattern, a predictive model of your space. That means you have to understand what patterns you're going to experience are going to recur, and thus you can start mapping cause and effect relationships and affective relationships and says, is this going to be good for me, bad for me, should I avoid it, should I approach it? You know, it's all based on that. And so at the synaptic level, these are coincidental events. These two neurons just fire. There's nothing up there saying, you know, that's a really good one, we should keep that one right off the bat. You know, the old view of a homunculus, the little man in the head that made all the real decisions about what was important, right? It doesn't work, but this is a problem. So here you're creating information, you're creating these synapses with no knowledge of whether it's going to be interesting or useful. So what happens is a superstition. Well, yeah, it is superstition. You don't have any proof, but you keep the information around, and in fact, you use it. But it's grounded superstition, and this is a really important point. You know, the symbol grounding problem in AI that's been around for a long time, you know, talked about the problem of building a symbolic system like a rule processing system that used kind of natural language words, but was really just doing kind of logical inference on the symbols. And then, you know, how does that apply back to a real system? And how do you keep that mapping going? In this system, and we believe in humans, every one of those synapses that form because two neurons actually fired. It's real experience. So it's grounded. It's not a lie. It just may not be very predictive. So if you look at all that, how does a system that's built this way going to function when it has this tsunami of superstition flying around? And the way that we believe it happens is by pulling the plug and opening the drain. So I mentioned these two effects that were going on. Talk about Hudenlockers. Thatcher's came up with this notion of cyclical cortical reorganization, and from his studies and looking at synaptic density in youths, he found that about every 4 years there was a major reorganization going on. So what's going on? Well, I can tell you one of those things is going on. It happened with me a lot faster than most people. You know, when I was this big, you know, my body worked real differently than when it's this big, especially when it's this big now. I'm glad that I occasionally forget my motor control theory, right, internally, because my body changed. But this evidence that shows that this kind of thing is happening not only in a continual way, because obviously we don't remember every bit of input that hits our brain, right? There's roughly somewhere between half a petabyte and 10 petabytes of visual information that hits your visual cortex every day. Okay, we don't remember all that, right? You won't remember half of this tomorrow, even close to that. So, you know, how does this thing happen? It happens in waves, it happens continuously. How does that help us? So, you know, you take these two things together. Does this mean general intelligence? Not really, but we're getting there a lot faster than we expected. We applied these things to the metasemantic network in Joshua. This grounded superstition notion became a source, a very hyper-productive source of new concepts and associations and memories and effectively, you know, content. And at the same time, we vented that combinatorial explosion of kind of superstitious information with very aggressive forgetting. And what you end up with is a race between this kind of very optimistic view of your experience and very quickly kind of culling everything that doesn't meet a certain threshold. And this kind of continuous flow creates a very interesting system that allows you to kind of get a view to autonomously adapt in this context of experience and emotional control. And without a homunculus, it can do it on its own just based on its experience. So the project actually was in full-time development between 2000 and 2002. We created a lot of interesting questions. We had a lot of interesting results, some interesting algorithms. One, we definitely need hardware to kind of come up underneath our algorithms to run these things in closer to real time. The question earlier about multi-core and mini-core processors is, in fact, something I'm going to be working on the next couple of years, because right now, all this new architecture we have, we don't know how to program it effectively. So to be able to actually exploit that technology, we've got to go solve some intermediate problems in programming it. But we also looked at, in this developmental model, not doing it in physical robotics, but in virtual systems. And so the idea there is you need a high fidelity enough virtual system where you can have a high fidelity body representation with lots of sensors and actuators to be able to put one of these systems in and let it learn. The other thing we came up with was a lot of interesting questions. Like one of the big ones is we found we needed in our system a much more flexible model of experience that accounts for the temporal warping that goes on in human cognition when it's thinking about its own processes. when it's looking at some cause and effect chain that it's experienced, and our system could do that, how does it allow that to stretch and compress and still do the kind of pattern matching to let you figure out that maybe you ought to try this thing again? So, to sum up, the pathway to artificial general intelligence, right? Everyone has their favorite one. This is mine. We found following the child, looking at childhood development, taking it seriously, go across campus and talk to the psychology department, talk to the neurophysiology department, find out what they've been learning, and then use your engineering skill to try to build analogs of that in the system. Thank you.
Okay, so we'll take a few questions. Yeah, right there, Sam. Yeah, go ahead.
Go ahead.
Yeah, I'm curious how you decided to teach it how to forget. Did you use a Bayesian course, or was there more of a look at how people do it?
The question was, how did we teach it how to forget? Did we use Bayesian approaches or some other kind of approach that was more like humans? We actually created a system that used this kind of cyclical reorganization technique. So we actually had, in this kind of semantic network we had, so you're creating new nodes, which are concepts and associations, and they varied in strength, and they were impacted by emotion. There were all kinds of things about how it got created. But they also had a measure that was sort of similar to long-term potentiation in neurons. So we would measure that, and we would say occasionally, we'd say, okay, if you haven't reached a certain level of potentiation, in other words, you haven't reoccurred enough to be a potentially good model of what's going on out there in the environment, we'll get rid of you. So we kind of emulated these large-scale cortical events, but we did it in much more compressed ways. And there were some interesting questions about how frequently you do that, at what scale it happens, lots of interesting parameters to tweak to figure out how to do it right. Other questions? You gonna
Yeah, down
target
here.
him?
Ben, go ahead.
Yeah, so
Oh, hi, Ben.
my question is, if there were funding to continue the project
Yeah.
now, would you consider it worthwhile to put a theory and engineering effort into it now without waiting for more hardware? Or do you really feel like you need to wait for hardware development in order to go on with this project?
The question was, if funding wasn't an issue, would we want to keep going with it right now, or do we really think it's going to take a little more development in areas like hardware? I really think it's going to take some more development. We have some very interesting things. If we were to go ahead and actively develop it now, we could produce some interesting results. But remember, the goal that we were shooting for was an AGI. And so when we looked at some of the problems of how a system learns, say, for instance, cause and effect relationships in its environment, which we thought was a very key attribute, we had to have something a lot more flexible. So there's some theoretical work that we need to do and some modeling work we need to do as well, which is good because it's going to take a few more cranks. The system that we had was incredibly primitive in that the number of sensors and actuators that we were actually able to support and get any kind of cycle time on the simulation was tiny, on the order of handfuls, not the tens of thousands or millions that you might want in a really rich simulation. So we really are going to need the hardware to get there. But funding's great too. We'll take any that you have. Oh, we can't. No, we're supposed to give you funding. Yeah, you're with the Institute. Okay. Other questions? All the way back. Who's? How do you ground your research? What are the kinds of things you try to make it do? Well, one thing that we didn't do was try to have really rich models of sensor actuator systems like humans. So, we're not trying to model audition or vision or something like that in a high way. We were really focused more on the kind of central cognitive capabilities. But one way that we grounded it in the kind of testing we did initially, is we said, like, if you look at a human infant, it has some innate behavior that it's going to do all by itself, kind of by default. We've all noticed what happens when a baby isn't happy, right? It starts squirming, eventually it starts crying and screaming, and it evokes hopefully a positive response from its environment that helps it start learning that, screaming is a great way to get attention. So one of the things you can look at, an early kind of test, even on very primitive systems, is you give them that kind of capabilities. These things have a simulated physiology. They have simulated kind of pain and pleasure and valence and arousal, which is similar to the Kismet emotional model. And so when it starts really feeling bad about its situation, it starts poking its environment. So you could see what a normal kind of non-intelligent response would be, which is just really kind of autonomic, going on the processes. what we'd like to be able to use to see when we're really getting learning is we take that curve of normal kind of response that's non-intelligent, when we see that curve changing, and we can obviously go inside and look at this. It's one of the differences between our approach and, say, neural nets is you can actually crack the thing open and understand what's in there. So, we look at the variance between kind of autonomic processes in a complex system like these models, and then intelligent processes and how you measure the difference between them. And then we start looking at things like, psychological measures. Well, what kind of test are we trying to execute? Really simple one. Do something besides just sit there and cry. Realize that there's some other behavior you can do because you've learned a little bit about your environment and a little bit about yourself that changes your situation enough that you don't just kind of give up and thrash and cry. Okay, I think that's it. Thank you. My pleasure.